All right, so to understand what's going on here, let me create this imaginary function we had. Okay, so here is this point at C, and let's just go a little bit away from C. We'll go delta x. So this is C plus delta x, and that's going to yield another point here. So the difference between these two, we call that delta y. So the change in y, and delta y is right here. It's just the y value of this point, f of c plus delta x, minus the y value at this point, which is just f of c. So that's what this is. Now, we may not know that, okay? So trying to find that delta y can sometimes be a little challenging on the function. So instead, we might decide that we want to look at the tangent line approximation, okay? So instead, we want to look at this tangent line, and this other point here, it won't be exactly, but it's going to be really, really close. So if we use that tangent line approximation, that's the tangent line. And then this x minus c, that's just your delta x. So we can use that tangent approximation to find what we call dy. So it's going to approximate that change in y, but to do it on the line instead of on the actual function. So we call the delta y a differential of y, and we call delta x a differential of x. So the two really key things that we want to have is right here, delta y. That is on the actual function. And like I said, often we can't find that, but what we can find is dy. And that's the change in y on the tangent line. And if we're close enough to the point, if we're close enough to this point, delta y and dy are essentially the same thing, and we can use them as substitutions for each other. Okay, so those are the two formulas that you need to know to be able to work with. Okay, delta y is just f of c plus delta x minus f of c. It's a y minus y. And then dy is the change on the tangent line. And we get that tangent line from the slope, the derivative f of x times dx. So let me show you an actual problem with this. So we want to find, on the function y equals x squared, we want to find dy when x is 1 and dx is 0.01, and then we want to compare that with delta y for the same thing. Okay, so remember, told you that dy is from the tangent line, so we have the slope times delta, the change in x, dx. And then delta y, it comes from just the change, it's just a y minus y, like this. Okay, so let's first look at dy. So the first thing that we need to find is the derivative of x. So the derivative of x squared is 2x dx. And then we want to plug in the point. X is 1 and dx is 0.01. So that tells us that dy is 0.02. Okay, so what that is remember we have a parabola, and at this point 1, 0, we were looking at the tangent line. Okay, and as we go away from it a tenth, our y value changes, a hundredth, our y value changes 200. Okay, and that tells us how far apart those y values are on the tangent approximation. Now, we can do the same thing with the actual points here and here. Okay, and that's delta y. So delta y is going to be f of c. C is just our x value, 1. Delta x is the same thing as dx. So 0.01 minus f of c, which we're at the 0.1. So now we want to plug that in. So f of 1.01, we're just plugging that into the function. So it's 1.01 squared minus, we're plugging 1 into the function, 1 squared. And when we do that, we're going to grab our calculator. We get 0.0201. Okay, so that is the change in y between these 2 points on the actual function. And notice those two values are really, really similar, okay, because we're not very far away from that point, okay? In tomorrow's lesson, we'll see the practical applications of this, but we'll do a little bit more with differentials in the next video.